Welcome back to the Deep Dive. Today we are diving into the fascinating world of physics, specifically a groundbreaking discovery. We're going to be talking about a new phase of matter that scientists have discovered.
It is pretty exciting stuff.
So, when we think about phases of matter, we typically think about things like solid, liquid, gas. But there's a whole lot more out there.
Oh, yeah, there are tons and tons of exotic phases of matter that we don't typically think about.
Right. And this one's called half ice, half fire.
It's a very cool name.
It's a very evocative name, and it was discovered by physicists Wei-Guo and Alexei Svelik at Brookhaven National Laboratory.
That's right.
We're going to be looking at an article that was published in Science X, and this article is based on research that was published in Physical Review Letters.
Cool.
So we're going to be trying to understand this new state of matter, how it was discovered, and why it's important to you, the listener, why you should care about this. So let's get started. Let's talk about this half ice, half fire concept. Can you explain what that even means?
Sure. So this new phase of matter is characterized by a unique arrangement of electron spins. So to kind of break that down a little bit, each electron has what we call spin. And you can kind of visualize it as like a little tiny magnet. Magnets have a north pole and a south pole, and they can point up or down.
Yeah.
And so in any material, you have a bunch of electrons, and these electrons are all kind of pointing in different directions. But in this particular case, the half-ice part refers to the fact that half of the spins are very ordered, so they're all pointing in the same direction.
Okay. So they're kind of frozen in place, like ice.
Exactly. And then the other half of the spins are totally disordered. So they're constantly fluctuating. They're pointing up, they're pointing down, they're pointing sideways. They're kind of doing their own thing. And that's the half-fire part.
So it's like you have this really rigid structure on one side and then just total chaos on the other side. And that's never been observed before.
Exactly. It's a completely new way that spins can arrange themselves. And what's really cool about it is that there's actually a visual representation of this in the Physical Review Letters paper. They show this graphical interpretation where you can kind of see like there's this area of the material that's really highly ordered, and then right next to it there's this area that's completely disordered.
Oh, wow. So you can actually visually see the difference between the two states.
That's right.
So why is discovering a new phase of matter such a big deal?
Well, it's a big deal because it's a really fundamental discovery. We're constantly trying to understand the universe better, and one way to do that is to understand the different ways that matter can behave.
Yeah.
And each new phase of matter that we discover has the potential to lead to new technologies, new applications that we haven't even thought of yet.
Okay. So what kind of technological implications could this half-ice, half-fire state have? I know the article mentions quantum computing and spintronics.
Right. So quantum computing is a really exciting new field of computing that uses quantum mechanics to perform calculations that are impossible for traditional computers.
Okay.
And spintronics is a field of electronics that uses the spin of electrons to store and process information.
Right.
And the really cool thing about this half-ice, half-fire state is that it could potentially be used in both of these fields because it has this unique combination of order and disorder.
Interesting.
And the fact that it can switch between these two states so easily means that it could be used to create new types of switches and memory devices.
So this sharp switching is really important, it sounds like.
Yeah, it is.
Okay. Let's talk about the half-fire, half-ice state, because the article mentions that this is a twin state of that. Can you explain what that means?
Right. So the half-fire, half-ice state was actually discovered earlier. And it's very similar to the half-ice, half-fire state, but the roles of the hot and cold spins are reversed. So in the half-fire, half-ice state, the hot spins are disordered with small magnetic moments, and the cold spins are ordered with large magnetic moments.
So it's kind of like the opposite of what we just talked about.
Exactly.
And they found that this half-fire, half-ice state exists in a magnetic compound called Sr3CuIr6. And it was induced by a magnetic field. But there was a bit of a puzzle there because the theoretical model that they were using to try to understand this didn't really predict this finite temperature phase transition. Can you explain that a little bit more?
Yeah, so the model is called the one-dimensional Ising model, and it's a really simplified model of magnetism. And it actually does predict the existence of the half-fire, half-ice state, but it doesn't predict that it can undergo a phase transition at any finite temperature. So that was a bit of a mystery because, the real world, materials do undergo phase transitions at finite temperatures.
Right. So the model didn't quite match up with what they were observing in the lab.
That's right.
And this is where Yin's work comes in because he showed that this forbidden phase transition could actually be approached through what's called an ultra-narrow phase crossover at a fixed finite temperature.
Exactly.
So he kind of found a way around that theoretical roadblock.
Yeah, he showed that, even though the model doesn't predict a phase transition, in the real world, it's still possible to get this sharp switching between the half-fire, half-ice state and the half-ice, half-fire state.
Okay. So how did they figure out that the half-ice state actually has this hidden opposite state?
Well, they did a lot of really careful experiments and calculations.
Hmm.
And what they found is that if you change the temperature just a tiny bit, like a fraction of a degree, the material will suddenly switch from the half-fire, half-ice state to the half-ice, half-fire state.
Wow. That's amazing. So it's incredibly sensitive to temperature changes.
It is, and that's what makes it so potentially useful for things like refrigeration and information storage.
Okay, so let's talk about those applications. How could this half-ice, half-fire state be used for refrigeration?
Well, as I mentioned before, when the material switches between the half-fire, half-ice state and the half-ice, half-fire state,
Hmm.
it undergoes a huge change in its magnetic entropy.
Right.
And entropy is a measure of disorder.
Okay.
So when the material switches from the half-fire, half-ice state, which is more disordered, to the half-ice, half-fire state, which is more ordered, it releases a lot of heat.
Right.
And if you can control this switching process, you can use it to create a very efficient refrigerator.
Oh, wow.
So you could have a material that's in the half-fire, half-ice state, and then you apply a magnetic field to it, and it switches to the half-ice, half-fire state, and it releases a lot of heat, and that cools down whatever you want to cool down.
Yeah.
And then you remove the magnetic field, and it switches back to the half-fire, half-ice state, and it absorbs heat from the environment.
So it's a very elegant way of doing refrigeration.
Yeah, it is. It's much more efficient than traditional refrigeration technologies.
Okay. And how could it be used for information storage?
So as I mentioned before, the fact that the material can switch between these two states so easily means that it could be used to create a new type of memory device.
Okay.
So you could imagine having a material that's in the half-fire, half-ice state representing a 0, and then you apply a magnetic field to it, and it switches to the half-ice, half-fire state representing a 1.
Right.
And then you can read out the state of the material by measuring its magnetic properties.
Interesting. So it's a very compact and energy-efficient way of storing information.
Yeah, it is. And it's also potentially much faster than traditional memory devices.
That's amazing. So what's next for this research? What are Yin and Civelek planning to do?
Well, they want to explore this fire ice phenomenon in systems with quantum spins and other degrees of freedom.
Okay.
So they're basically trying to understand how this phenomenon works in more complex systems.
Right.
And they think that this could lead to even more exciting discoveries and applications.
So this is just the beginning of a whole new area of research.
Yeah, it is.
That's very exciting. So we've learned a lot about this half-ice, half-fire state of matter, and it sounds like it has the potential to really revolutionize a lot of different technologies.
Yeah, it does.
From refrigeration to information storage, and who knows what else we'll discover in the future.
It's really exciting stuff.
It is, and it's a great example of how fundamental research can lead to really practical applications that can benefit everyone. So thanks for joining us on this deep dive into the half-ice, half-fire state of matter, and we'll see you next time for another fascinating exploration of the world around us.
See you then.